The story of glass begins with sand. Sand rests quietly on beaches and in deserts, accumulating over vast stretches of time. Each grain of sand is small and rounded, worn smooth by wind and water over countless years. The sand lies still under the open sky, warmed by the sun during the day and cooling as night arrives. This sand, so common and unremarkable, holds within it the potential to become something entirely different. The sand used for making glass is not just any sand. It is a particular kind of sand, one that contains high amounts of silica. Silica is a compound made of silicon and oxygen, and it forms the foundation of what glass will become. The sand appears pale and clean, sometimes almost white, sometimes with hints of color from other minerals mixed within it. This sand has been deposited over long periods, settled in layers, compressed and shifted by natural forces. When sand is chosen for glassmaking, it is gathered from quarries or mines where it has accumulated in pure deposits. The sand is extracted carefully, loaded into trucks or containers, and transported to facilities where it will be transformed. The journey from the earth to the factory is the first step in a process that will change the sand completely, turning something grainy and solid into something smooth and transparent. At the factory, the sand arrives and is stored in large containers or silos. It waits there, dry and still, until it is needed. The sand particles are uniform in size, having been sifted and sorted to remove anything too large or too small. Consistency matters in glassmaking, and so the sand must be prepared carefully before it can be used. The sand rests in storage, unchanged for now, simply waiting for the next stage. To the sand, other materials are added. Soda ash is one of these materials, a white powder that will help lower the temperature at which the sand melts. Limestone is another addition, contributing stability to the final glass. These materials are measured and mixed together with the sand, creating a batch of raw ingredients that will be melted together. The mixing happens slowly, with the powders and granules tumbling together until they are evenly distributed. The mixture of sand, soda ash, and limestone is sometimes called batch. The batch sits in containers, waiting to be fed into the furnace where the transformation will truly begin. The batch looks unremarkable, just a pale mixture of powders and grains. Nothing about its appearance suggests the clear, smooth material it will become. But the potential is there, locked within the chemical bonds that hold the materials together. The furnace is a large structure built to withstand extreme heat. It is lined with special bricks that can endure temperatures far beyond what ordinary materials could survive. The furnace is already hot when the batch is introduced, glowing with heat that radiates outward. The temperature inside is measured and controlled carefully, maintained at a level high enough to melt the batch completely. The batch is fed into the furnace slowly and steadily. It enters the intense heat and begins to change almost immediately. The particles of sand and the other materials start to break down as the heat works on them. The solid grains soften first, their edges beginning to blur. As the temperature continues to rise, the materials begin to melt, losing their individual forms and starting to flow together. The melting process takes time. The batch does not transform instantly but gradually, as heat penetrates every particle and breaks apart the structures that held them solid. The sand loses its graininess. The soda ash and limestone dissolve into the mixture, and slowly, everything combines into a single molten mass. This molten material glows with heat, orange and bright, flowing slowly like thick honey. The molten glass is denser than it will be when cooled, and it moves with a heavy, deliberate quality. It pools at the bottom of the furnace, gathering in a reservoir of liquid heat. Bubbles sometimes form within the molten glass, small pockets of gas that rise slowly through the thick liquid and eventually burst at the surface. The glass remains in the furnace, kept at high temperature, until it is needed for the next step. Within the furnace, the molten glass is in constant slow motion. Currents move through the liquid as heat rises from below and cooler areas form near the surface. The glass circulates gently, mixing itself, ensuring that the composition remains uniform throughout. This motion is subtle, almost imperceptible, but it is continuous as long as the glass remains molten. The furnace operates continuously in many glass factories, never cooling down, never stopping. The molten glass is maintained at a consistent temperature day and night, ready to be shaped whenever needed. Fresh batch is added periodically to replace the glass that is removed for forming, and the furnace continues its work without pause. The heat is constant, the glow of the molten glass never fading. When glass is ready to be formed, it must be removed from the furnace in a controlled way. The temperature of the molten glass is crucial at this stage. If it is too hot, it will be too fluid and difficult to control. If it has cooled too much, it will be too stiff and resist shaping. The glass must be at exactly the right temperature, a state where it is soft enough to be molded but thick enough to hold some shape. There are many methods for forming glass, each suited to different products and purposes. One of the oldest methods involves gathering molten glass on the end of a long metal pipe. The pipe is dipped into the molten glass in the furnace, and a portion of the liquid glass adheres to the end. The glassworker rotates the pipe slowly, allowing the glass to gather evenly around the opening of the pipe. The gathered glass glows with heat, orange and bright, dripping slightly as gravity pulls on the molten material. The glassworker must move steadily and deliberately, keeping the pipe rotating so that the glass does not sag to one side. The rotation is continuous and smooth, a gentle turning that maintains the balance of the molten gather. Once a sufficient amount of glass has been gathered, the glassworker can begin to shape it. The pipe is removed from the furnace and held horizontally, still rotating. The glassworker may blow gently into the pipe, introducing air into the molten glass. The air creates a bubble within the glass, and as more air is added, the bubble expands, pushing the glass outward from within. The expanding bubble causes the glass to inflate like a balloon, growing larger as air fills the interior. The walls of the glass become thinner as it expands, stretched by the pressure of the air inside. The glassworker controls the expansion by regulating how much air is blown and how quickly, shaping the glass into a hollow form. The process is slow and requires patience, as rushing would cause the glass to expand unevenly or collapse. As the glass cools, it becomes less fluid and more resistant to shaping. The glassworker must sometimes reheat the glass by placing it back near the furnace opening, warming it again so that it remains workable. This cycle of shaping and reheating can be repeated several times as the piece is gradually formed. Each time the glass is reheated, it glows bright again, and each time it is removed from the heat, it begins to cool and stiffen once more. Tools are used to shape the glass more precisely. Wooden blocks soaked in water can be pressed against the hot glass to smooth its surface and shape it. The water on the wood evaporates instantly when it touches the glass, creating a cushion of steam that prevents the wood from burning. The tool presses gently against the glass, guiding it into the desired form. Metal tools can also be used to manipulate the glass. Shears can trim away excess glass, while paddles can flatten areas or create specific shapes. Tweezers can pull and stretch the glass, forming handles or spouts or decorative elements. Each tool interacts with the glass in a particular way, and the glassworker chooses tools based on what shape is being created. The forming process is a continuous dance between heat and cooling, between soft malleability and increasing stiffness. The glass is never entirely solid during this stage, always retaining some ability to move and change, but it is also never as fluid as it was in the furnace. It exists in a transition state, neither fully liquid nor fully solid, and this is the state in which it can be shaped. When the glass has been formed into the desired shape, it must cool slowly and carefully. Glass that cools too quickly can develop stresses within its structure, creating weaknesses that might cause it to crack or shatter later. To prevent this, the formed glass is placed in an annealing oven, also called a layer. The layer is kept at a temperature high enough that the glass remains slightly soft but not so hot that it will deform. Inside the annealing oven, the glass rests as it begins its slow cooling process. The temperature in the oven is lowered gradually, degree by degree, over a period of hours or even days depending on the thickness and size of the glass piece. This controlled cooling allows the internal structure of the glass to relax and stabilize without developing the stresses that rapid cooling would create. The glass sits quietly in the layer, glowing faintly at first as it retains heat from the forming process. As time passes and the temperature decreases, the glow fades until the glass appears dark, though it is still too hot to touch. The cooling continues even after the visible glow has disappeared, with heat gradually dissipating into the surrounding air. During the annealing process, the molecular structure of the glass settles into its final arrangement. Glass is not a crystalline solid like many materials but rather an amorphous solid, meaning its molecules are not arranged in a regular repeating pattern. Instead, they are frozen in a disordered state, similar to a liquid but locked in place. The slow cooling of annealing allows this disordered structure to settle without creating internal tensions. When the glass has finally cooled to room temperature, it can be removed from the annealing oven. The glass is now hard and rigid, no longer capable of being shaped by hand or simple tools. It has become the transparent, brittle material that is familiar in everyday life. The transformation from molten liquid to solid glass is complete. The glass at this stage may require additional finishing. Rough edges where the glass was separated from the pipe or where excess was trimmed away may need to be smoothed. This is done by grinding the glass against abrasive materials that wear away the rough areas gradually. The grinding process is methodical, with the glass moved against the abrasive in steady, even motions. After grinding, the glass may be polished to restore clarity to any areas that became clouded during grinding. Polishing involves using finer and finer abrasives, each one removing the scratches left by the previous one, until the surface is smooth enough to be perfectly transparent again. The polishing process is patient and thorough, each stage preparing the glass for the next finer treatment. Some glass products are made not by blowing but by other forming methods. Float glass, which is used for windows and many other flat glass applications, is made by floating molten glass on a bath of molten tin. The glass spreads out across the surface of the tin, forming a flat sheet with parallel surfaces. The glass floats because it is less dense than the molten tin beneath it. The molten glass is poured onto one end of the tin bath and flows across the surface, spreading and thinning as it moves. The tin bath is enclosed in a controlled atmosphere to prevent oxidation, and the temperature is carefully regulated to keep both the glass and the tin in their molten states. The glass flows slowly across the tin, gradually cooling as it moves toward the far end of the bath. As the glass cools on the tin bath, it begins to solidify while still maintaining its perfectly flat and parallel surfaces. The tin provides a smooth support that gives the glass its flat form. The glass does not stick to the tin because the two materials do not bond chemically. When the glass has solidified enough to hold its shape, it is lifted off the tin bath and moved into an annealing layer. The ribbon of glass that emerges from the float process is continuous, like a river of glass flowing steadily from the furnace. It moves on rollers through the annealing layer, cooling gradually as it travels. The speed of the ribbon is controlled to match the cooling rate, ensuring that the glass spends the right amount of time at each temperature as it cools. After annealing, the continuous ribbon of glass is cut into sheets of usable size. Cutting is done with specialized tools that score the glass surface and then apply pressure to break the glass along the scored line. The break is clean and straight, creating edges that are sharp and precise. The sheets of glass are then stacked and packaged for shipment to customers who will use them in windows, mirrors, or other applications. Another method of forming glass involves pressing molten glass into molds. A portion of molten glass is gathered and placed into a metal mold that has been shaped to create a specific form. A plunger then presses down into the molten glass, forcing it to fill the mold cavity and take on the shape of both the mold and the plunger. The pressure must be applied steadily and evenly to ensure the glass fills every part of the mold. The mold is usually made of metal and may be coated with a release agent to prevent the glass from sticking. The metal absorbs heat from the molten glass, helping it cool and begin to solidify. As the glass cools, it becomes rigid enough to hold the shape of the mold. The pressing process is relatively quick compared to blowing, making it suitable for producing many identical pieces. When the glass has cooled sufficiently in the mold, it is removed and transferred to an annealing oven. The pressed piece has taken on the detailed shape of the mold, with any textures or patterns from the mold surface now impressed into the glass. The piece may require some finishing to remove excess glass or smooth rough edges, but the basic form is complete when it comes out of the mold. Glass bottles and jars are often made using a combination of blowing and molding. Molten glass is gathered and placed into a blank mold, where it is partially formed into a rough shape. Air is then blown into the glass to expand it against the walls of the blank mold, creating a preliminary form called a parison. The parison is then transferred to a final mold where additional air pressure expands it into the finished bottle or jar shape. The bottle-making process is automated in modern factories, with machines performing each step in rapid succession. Molten glass is cut into precise portions called gobs, which are delivered to the forming machines. The machines work continuously, producing bottles at a steady rate, each one identical to the last. The bottles move through the process on conveyors, being formed, annealed, and inspected before being packed for shipment. Throughout all these forming methods, the essential nature of glass remains the same. It begins as a molten liquid, is shaped while in a softened state, and is then cooled carefully to preserve the shape and prevent stress. The methods differ in their specific techniques, but they all rely on controlling temperature and using the unique properties of glass in its softened state. Glass can also be colored by adding certain metallic compounds to the batch before melting. Cobalt oxide creates blue glass. Iron oxide can create green or brown glass depending on the amount used, and copper oxide can produce turquoise or red glass. The metal compounds dissolve in the molten glass and give it color that remains after cooling. The color is uniform throughout the glass, not just on the surface. Clear glass is actually the most difficult to produce because any impurities in the raw materials can create unwanted color. Iron is a common impurity in sand, and even small amounts can give glass a greenish tint. To make truly clear glass, the sand must be very pure, or decolorizing agents must be added to counteract the tinting effect of impurities. The pursuit of perfectly clear glass has driven much innovation in glassmaking. Once glass has been formed and annealed, it can undergo additional treatments to change its properties. Tempering is a process that makes glass much stronger and changes how it breaks. To temper glass, it is heated to a high temperature and then cooled very rapidly by blasting it with air. The rapid cooling causes the outer surfaces to solidify while the interior is still soft. As the interior continues to cool and contract, it pulls on the already solid outer layers, creating compressive stress in the surface and tensile stress in the interior. This stress pattern makes the glass much stronger than ordinary glass because the surface compression must be overcome before the glass can break. Tempered glass is used in applications where strength and safety are important, such as car windows and glass doors. When tempered glass does break, the internal stresses cause it to shatter into small, relatively harmless pieces rather than large sharp shards. The entire piece breaks at once, fragmenting throughout its structure. This breakage pattern makes tempered glass safer than ordinary glass in situations where breakage might occur. Laminated glass is another type of safety glass, made by bonding layers of glass together with a plastic interlayer. The glass layers are cut to size and cleaned thoroughly to remove any dust or contaminants. A sheet of plastic, usually polyvinyl butyryl, is placed between the glass layers. The assembly is then placed in an oven where heat and pressure bond the layers together. The plastic interlayer holds the glass fragments in place if the glass is broken, preventing the shards from scattering. This makes laminated glass useful for car windshields and other applications where containing broken glass is important. The plastic layer is transparent, so the laminated glass remains clear while providing added safety. Glass can be decorated or modified in many ways after forming. Etching involves treating the glass surface with acid or abrasive materials to create a frosted appearance or pattern. The areas to be etched are exposed while other areas are protected by a resistant coating. The acid or abrasive removes a thin layer of glass from the exposed areas, leaving them rough and translucent rather than smooth and transparent. Sandblasting is a type of abrasive etching where fine particles are propelled at high speed against the glass surface. The particles chip away tiny fragments of glass, creating a frosted texture. Masks or stencils protect areas that should remain clear, while exposed areas are blasted. The depth and texture of the frosting can be controlled by adjusting the particle size and blasting pressure. Glass can also be painted or coated with thin films to change its appearance or properties. Metallic coatings can be applied to create mirrors or to reduce heat transmission through windows. The coatings are often applied in a vacuum chamber where vaporized metal condenses on the glass surface in an extremely thin layer. These coatings are measured in fractions of wavelengths of light, yet they dramatically change the glass's properties. Some glass is decorated with printed patterns or colors. Special inks or paints that can withstand the heat of the tempering process are applied to the glass surface. The glass is then heated, and the decoration fuses permanently to the surface. This allows for colored or patterned glass that will not wear away with use or cleaning. The recycling of glass is simpler in some ways than recycling many other materials. Glass can be melted and reformed repeatedly without losing its essential properties. Recycled glass, called cullet, can be added to the batch along with virgin raw materials. The cullet melts at a lower temperature than the raw materials, which can reduce the energy needed for melting. Glass for recycling is collected and sorted by color because different colors cannot easily be mixed without affecting the final product. Clear glass must be kept separate from colored glass to maintain its clarity. The sorted glass is cleaned to remove any contaminants like labels, caps, or non-glass materials. The clean glass is then crushed into small pieces, creating cullet ready to be melted. The cullet is mixed with the batch in proportions that depend on the desired product and available materials. In some cases, glass can be made entirely from cullet, though usually some virgin materials are included to ensure consistent quality. The mixture is melted in the furnace just like a batch made entirely from raw materials, and the resulting glass is indistinguishable from glass made without recycled content. The versatility of glass has made it essential in modern life. It is used in windows that allow light into buildings while providing protection from weather. It forms containers that preserve food and beverages without affecting their taste. It creates lenses that correct vision and enable scientific instruments. It insulates electrical components and transmits light in fiber optic cables. Each application takes advantage of specific properties of glass. Windows use glass's transparency and ability to form large flat sheets. Containers use glass's impermeability and chemical inertness. Lenses use glass's ability to refract light in precise ways. Fiber optics use glass's transparency to specific wavelengths and its ability to be drawn into fine threads. The variety of glass types and forms allows it to serve all these different purposes. The production of glass fiber for insulation or reinforcement follows a different path than glass for most other uses. Molten glass is allowed to flow through small holes in a container, forming thin streams. These streams are drawn downward by gravity or by mechanical pulling, stretching them into extremely fine fibers. The fibers cool rapidly as they are drawn, solidifying while still in their elongated form. The glass fibers are collected and can be used in various ways. For insulation, they may be gathered into loose mats that trap air and provide thermal resistance. For reinforcement, they may be woven into fabric or combined with resins to create composite materials. The strength of the individual fibers comes from their thinness and the way stress is distributed through their structure. Optical fibers for telecommunications are made from extremely pure glass that must be free from any impurities that might absorb or scatter light. The glass is formed into a preform, a thick rod with precisely controlled composition. The center has one composition that will become the core of the fiber, while the outer layer has a slightly different composition that will become the cladding. The preform is heated until the glass softens, and then the end is pulled downward, drawing out a fiber that maintains the core cladding structure of the preform but at a much smaller diameter. The fiber is drawn continuously, with the preform feeding into the heat zone at one end and the fiber emerging from the bottom and being wound onto a spool. The diameter of the fiber is controlled precisely to ensure it meets the specifications needed for transmitting light. The fiber that emerges is hair-thin and flexible, capable of being bent without breaking if the bending radius is not too sharp. Light travels through the core of the fiber, and the cladding keeps the light contained through the principle of total internal reflection. This allows light signals to travel long distances through the fiber with minimal loss, making fiber optic communication possible. Glass used in scientific applications often requires special compositions to give it particular properties. Laboratory glassware is usually made from borosilicate glass, which contains boron oxide in addition to the usual silica, soda, and lime. The boron oxide makes the glass more resistant to thermal shock, meaning it can withstand rapid temperature changes without cracking. This property is essential for glass that will be heated or cooled during experiments. The making of borosilicate glass follows the same general process as other glasses, but the batch composition is adjusted to include the boron compound. The melting and forming processes are similar, though the working properties of the molten glass may differ slightly from standard glass. The resulting glass looks similar to regular glass but behaves differently when exposed to heat. Lead glass, also known as crystal, contains lead oxide which gives it different properties from ordinary glass. Lead glass is softer than regular glass and can be cut and polished more easily to create decorative patterns. It also has a higher refractive index, meaning light bends more when passing through it, creating more brilliance and sparkle. Lead glass is heavier than ordinary glass due to the density of lead. The production of lead glass requires careful handling of the lead compounds used in the batch, as lead can be hazardous. The melting process is similar to other glasses, but the resulting molten glass has different flow characteristics. Lead glass cools more slowly than ordinary glass and remains workable at lower temperatures, which can be advantageous for hand-forming and detailed work. Art glass encompasses a wide variety of decorative glass objects made using many different techniques. Some art glass is formed by blowing, with the artist shaping the molten glass using traditional tools and methods. The artist may add color by applying bits of colored glass to the surface while the piece is being formed, or by using colored glass from the start. Fused glass art involves arranging pieces of glass on a flat surface and then heating them in a kiln until they soften enough to fuse together. The pieces are cut from sheet glass in various colors and arranged in a pattern or design. When heated, the edges soften and merge, creating a single piece with the design incorporated throughout. The firing temperature and time determine how much the glass flows and how distinct the boundaries between colors remain. Slumping is a related technique where glass is heated over or in a mold and allowed to sag into the mold's shape under gravity. The glass softens in the heat but does not become fully molten, so it slowly conforms to the mold while retaining its surface texture and any patterns or colors it had before firing. Slumped glass can create bowls, dishes, or sculptural forms. Stained glass windows are assembled from pieces of colored glass held together by metal strips. Each piece of glass is cut to a specific shape that fits into the overall design. The edges of the glass pieces are wrapped with copper foil or fitted into channels in lead strips called came. The metal is then soldered at the joints, creating a network that holds all the pieces in their positions. The colors in stained glass come from metallic compounds added during glassmaking, just as with other colored glass. The pieces are selected for their colors and sometimes for their textures, as stained glass often has variations and patterns within each piece that add visual interest. When light shines through a stained glass window, the colors glow and project patterns of colored light into the space beyond. Glass can be cast by pouring molten glass into a mold and allowing it to cool and solidify in the mold's shape. This is different from pressing, where the glass is forced into the mold under pressure. Cast glass takes on all the details of the mold, including any texture or pattern on the mold's surface. Large cast glass pieces may take days or weeks to cool slowly enough to avoid cracking from internal stress. The lost wax technique can be used with glass just as it is with metal casting. A model is made in wax and a mold is formed around the wax model. The mold is heated, causing the wax to melt and drain away, leaving a cavity in the shape of the original model. Glass is then melted and poured into the cavity, filling the space where the wax had been. After cooling, the mold is broken away to reveal the glass casting. Pot de verre is a technique where crushed glass is mixed with a binder and packed into a mold. The mold is then fired in a kiln, causing the glass particles to fuse together while the binder burns away. The result is a glass object with a texture that may be slightly granular, different from the smooth surface of blown or molten glass. The technique allows for control over color gradation and surface texture. Glass blowing has been practiced for thousands of years, with techniques passed down through generations of artisans. The basic principle of gathering molten glass on a pipe and shaping it through blowing and tools remains the same, though modern glassblowers may use electric or gas furnaces instead of wood-fired ones. The skill required to control the glass and create consistent forms comes from long practice and experience. A glassblower must understand how glass behaves at different temperatures and how quickly it cools. The glass is constantly changing as it cools, becoming stiffer and less responsive to shaping. The glassblower works with this progression, timing each action to happen when the glass is at the right temperature and consistency. Reheating extends the working time but must be done carefully to maintain the form that has already been established. Teams of glassblowers may work together on larger or more complex pieces, with each person performing specific tasks in sequence. One person might gather the glass, another might blow the initial bubble, while others shape, add decorative elements, or transfer the piece between tools and equipment. The coordination between team members must be precise, as the timing of each step affects the success of the whole process. The tools used in glassblowing are relatively simple but require skill to use effectively. The blowpipe itself is a hollow metal tube that allows air to be blown into the molten glass. Puntais are solid metal rods used to hold glass pieces by attaching to their base, allowing the opening to be finished without the blowpipe in the way. Jacks are large tweezers used to shape necks, create indentations, or pull out decorative elements. Wooden blocks and paddles, kept wet to prevent burning, are used to shape the exterior of blown glass. The wet wood creates a thin layer of steam when it contacts the hot glass, allowing the tool to press and smooth the surface without sticking. The glassblower rotates the pipe constantly while using these tools, so the shaping happens evenly around the entire circumference of the piece. Shears are used to cut away excess glass or trim openings to the desired size. The cut must be made while the glass is at the right temperature, soft enough to cut but not so hot that it flows back together after being cut. The timing of the cut is part of the glassblower's skill, learned through experience with how glass behaves at different stages of cooling. After a piece is completed, it must be separated from the blowpipe or punty. This is usually done by making a sharp temperature change at the point of attachment, which causes the glass to crack and separate. The piece is then immediately placed in an annealing oven to begin its slow cooling process. The separation point may leave a rough area called a pontil mark that might need to be ground smooth later. The annealing oven for hand-blown pieces allows the glass to cool slowly from the temperature at which it was worked down to room temperature. The cooling rate must be controlled to prevent thermal stress from building up in the glass. Thicker pieces require longer annealing times because heat escapes more slowly from their interiors. The annealing process for a large piece might take several days. Industrial glass production operates at a much larger scale than studio glassblowing, with furnaces holding tons of molten glass and machines forming thousands of pieces per hour. The principles remain the same, but the execution is automated and optimized for efficiency and consistency. Temperature, timing, and mechanical precision are controlled by computer systems that monitor and adjust the process continuously. In a container glass factory, the furnace is fed continuously with batch material, which melts and mixes with the molten glass already present. The furnace operates 24 hours a day for months or years at a time, stopping only for major maintenance. The continuous operation is more efficient than repeatedly heating and cooling, and it maintains consistent glass quality. The molten glass flows from the furnace to the forming machines through channels called forehearths. The forehearths are temperature-controlled zones where the glass can be conditioned to exactly the right temperature for forming. Cooling or heating elements along the forehearth adjust the glass temperature as it flows, ensuring it arrives at the forming machine at the optimal consistency. Gobs of molten glass are cut from the flowing stream at precise intervals and delivered to the forming machines. The gobs must be uniform in size and temperature to produce consistent bottles or jars. The cutting mechanism operates with mechanical precision, severing the glass stream and deflecting each gob into a delivery channel that guides it into the forming machine. The forming machines use molds and compressed air to shape the bottles through a two-step process. The gob enters the blank mold where it is partially formed and air is blown to create a hollow parison. The parison is then inverted and transferred to the blow mold, where final blowing expands it to the finished bottle shape. The entire cycle takes only a few seconds per bottle. After forming, the bottles are still hot and are transferred to a conveyor that carries them through an annealing layer. The layer is a long tunnel with carefully controlled temperature zones. The bottles enter at one end where the temperature matches their heat level from forming, and they travel slowly through zones of gradually decreasing temperature. By the time they exit the far end, they have cooled completely and are ready for inspection and packaging. Inspection of glass containers involves checking for defects that might affect their function or appearance. Automated inspection systems use cameras and sensors to detect cracks, thin spots, bubbles, or other flaws. Bottles that do not meet quality standards are rejected and recycled back into the batch. The acceptable bottles continue to packaging where they are prepared for shipment to customers. Flat glass production in a float line operates continuously, with molten glass flowing from the furnace onto the tin bath in an endless ribbon. The width of the ribbon is controlled by edge rollers that contain the glass and prevent it from spreading too wide. The thickness is determined by the balance between the rate at which glass is delivered and the speed at which the ribbon is drawn forward. The tin bath chamber is filled with a protective atmosphere to prevent the tin from oxidizing. Nitrogen and hydrogen are commonly used for this purpose, maintained at slightly higher than atmospheric pressure to keep oxygen out. The controlled atmosphere also prevents contamination of the glass as it forms on the tin surface. As the glass ribbon moves across the tin bath, it cools gradually from the temperature at which it was poured to a temperature at which it is solid enough to be lifted off. The temperature decreases in zones along the length of the bath, with each zone maintained at a specific temperature to control the cooling rate. The glass must cool slowly enough to avoid thermal stress but quickly enough to maintain production efficiency. Rollers lift the glass ribbon off the tin bath at the exit end and transfer it to the annealing layer. The layer for flat glass is similar in principle to that used for containers, but it is designed to handle the continuous ribbon of glass. The ribbon travels on rollers through the temperature-controlled zones, cooling gradually until it reaches room temperature. After annealing, the glass ribbon passes through inspection stations where its quality is checked. Any defects are marked so those areas can be removed when the glass is cut into sheets. The inspection may be automated, using cameras and computer vision systems to detect flaws, or it may involve human inspectors examining the glass. The goal is to identify any problems before the glass is cut and packaged. The continuous ribbon is cut into large sheets using automated cutting equipment. Cutting tools score the glass surface with a hardened wheel or diamond point, creating a weak line along which the glass will break cleanly. Pressure is then applied to bend the glass along the scored line, causing it to separate. The cutting is done with precision to create sheets of exact dimensions. The cut sheets are stacked on racks for storage or shipping. Spacers separate the sheets to prevent them from touching each other directly, which could cause scratching. The stacks are handled carefully to avoid damage, as even small edge chips can weaken the glass. The sheets may be packed in crates or on pallets with protective materials to ensure they arrive at their destination undamaged. Glass for special purposes may undergo additional processing after the basic forming and annealing. Coating processes can apply thin films to change the glass's properties. Low emissivity coatings reduce heat transfer through windows by reflecting infrared radiation while allowing visible light to pass. These coatings are applied in vacuum chambers where vaporized metals condense on the glass surface in layers only a few atoms thick. Tempering requires reheating the glass to near its softening point and then cooling it rapidly with jets of air. The process must be completed after any cutting or edge work has been done, because tempered glass cannot be cut or modified without shattering. The rapid cooling creates the stress pattern that gives tempered glass its strength and characteristic breakage pattern. Heat strengthening is similar to tempering but uses slower cooling rates, creating a glass that is stronger than ordinary glass but not as strong as fully tempered glass. Heat-strengthened glass breaks into larger pieces than tempered glass, which can be advantageous in some applications. The process is used when increased strength is needed, but the safety breakage pattern of tempered glass is not required. Laminating involves bonding glass sheets together with plastic interlayers. The glass is cut to size and the edges are sometimes ground or polished. The plastic interlayer is trimmed to match the glass dimensions. The layers are assembled with the plastic sandwiched between glass sheets, and the assembly is placed in an autoclave where heat and pressure bond the layers together permanently. The autoclave is a pressurized chamber that applies uniform pressure across the entire surface of the laminated assembly. The combination of heat and pressure causes the plastic interlayer to flow and bond to the glass, eliminating air bubbles and creating a clear, strong composite. The bonding process takes time to ensure complete adhesion throughout the entire panel. Insulating glass units consist of 2 or more panes of glass separated by a spacer and sealed around the edges. The space between the panes is filled with air or an inert gas like argon, which provides thermal insulation. The edges are sealed to prevent moisture from entering the space between the panes, which would cause fogging and reduce the insulating value. The assembly of insulating glass units requires precision to ensure proper spacing and sealing. The spacer is typically a metal or plastic frame that runs around the perimeter of the glass, maintaining a consistent gap between the panes. The spacer may contain a desiccant that absorbs any moisture trapped inside during assembly. The edges are sealed with specialized sealants that remain flexible while preventing air or moisture transfer. Glass in buildings serves many functions beyond simply allowing light to enter. It provides a barrier against weather while maintaining visibility. It can control heat gain or loss through reflective or low emissivity coatings. It can reduce noise transmission through lamination or insulating glass construction. The glass in a modern building is often a sophisticated assembly designed to meet multiple performance requirements. The installation of glass in buildings must account for the material's properties. Glass expands and contracts with temperature changes, so the mounting system must allow for this movement while still holding the glass securely. The edges of the glass should not be in direct hard contact with the frame, as stress concentrations at contact points can cause cracking. Resilient materials separate the glass from rigid frame components. Large glass panels in commercial buildings may be held by structural silicone sealant rather than mechanical fasteners. The sealant bonds the glass to supporting frames while remaining flexible enough to accommodate movement. The sealant must be applied carefully to ensure complete adhesion and adequate thickness. Testing ensures the bond will hold the glass securely under wind loads and other forces. Glass tabletops and shelves are usually made from tempered glass to provide safety and strength. The glass is cut to size and the edges are polished before tempering. Edge polishing removes sharp edges and creates an attractive finish. The tempering process creates the internal stress pattern that gives the glass its strength and safe breakage characteristics. Mirrors are made by applying a reflective coating to glass. The glass provides a smooth, flat surface that supports the coating and protects it from damage. The coating is usually a thin layer of metal, traditionally silver, deposited on the back surface of the glass. The metal layer reflects light, creating the mirror effect. The coating is protected by additional layers of paint or backing material. The production of mirror glass involves careful cleaning of the glass surface before coating application. Any dust or contaminants will create defects in the reflective coating. The coating is applied in a controlled environment, often using chemical deposition processes where metal ions in solution are reduced to form a continuous metal film on the glass surface. After the reflective coating is applied, it is usually covered with protective layers. Copper may be deposited over the silver to protect it from corrosion. Paint or backing material is then applied to protect the metal layers from physical damage and environmental exposure. The multiple layers work together to create a durable mirror that will maintain its reflective properties over time. Automotive glass includes windshields, side windows, and rear windows, each with specific requirements. Windshields are laminated to prevent the glass from fragmenting in an accident, keeping the structure intact even if the glass is broken. The lamination also allows the windshield to support the roof in a rollover and to keep occupants inside the vehicle during a crash. Side and rear windows in vehicles are typically made from tempered glass, which provides strength and breaks into small granular pieces rather than sharp shards. The tempering allows the glass to withstand impacts and temperature changes without breaking under normal conditions. When the glass does break, the small pieces are less likely to cause serious injury. The curved shapes of automotive glass are created by slumping or bending processes. Flat glass is heated until it softens and then allowed to sag over or into a mold that has the desired curved shape. Gravity pulls the softening glass into conformity with the mold. The process must be controlled carefully to achieve the correct curvature while maintaining uniform thickness. After forming, automotive glass may be tempered or prepared for lamination depending on its intended use. Windshields receive ceramic frit around their edges, a fired-on coating that provides a surface for adhesive bonding and protects the laminating adhesive from ultraviolet light. The frit also serves as a visual border and can hide the bonding area from view. Glass for electronics applications can be extremely thin and must meet precise specifications for flatness and surface quality. Display glass for screens is produced using specialized processes that create glass with minimal variation in thickness and exceptional smoothness. The glass may be chemically strengthened to increase resistance to scratching and breaking despite its thinness. Chemical strengthening involves immersing the glass in a bath of molten potassium salt. Potassium ions from the salt replace smaller sodium ions in the glass surface through an exchange process. The larger potassium ions create compressive stress in the surface layer, similar to tempering but achieved through chemistry rather than thermal treatment. The process can strengthen thin glass that cannot be tempered thermally without warping. Glass for pharmaceutical applications must be chemically inert and resistant to leaching substances into medicines. Borosilicate glass is commonly used because it does not react with most pharmaceutical compounds and can withstand sterilization processes. The glass is formed into vials, bottles, or ampoules that will hold injectable or oral medications. The production of pharmaceutical glass requires exceptional cleanliness to prevent contamination. The forming equipment must be maintained in pristine condition, and the glass is handled in controlled environments. After forming and annealing, the glass containers may be washed and sterilized before being filled with medication. Quality control ensures that each container meets strict specifications. Laboratory glassware includes beakers, flasks, test tubes, and many other items used in scientific work. Most laboratory glass is borosilicate because of its thermal shock resistance and chemical durability. The glass can be heated directly over flames or in ovens without cracking, and it resists corrosion from most chemicals used in laboratories. Precision laboratory glassware such as volumetric flasks and graduated cylinders must meet exact volume specifications. The glass is formed and then carefully calibrated, with markings applied to indicate precise volumes. The accuracy of these markings is essential for quantitative work in chemistry and biology. Each piece may be individually tested to verify its accuracy. Glass tubing and rods are made by drawing processes where molten glass is formed into a continuous tube or rod and drawn to the desired diameter. For tubing, air is blown through the center to maintain the hollow core as the glass is drawn. The diameter of the tube or rod is controlled by the speed of drawing and the amount of glass fed into the process. The continuous product is cut into manageable lengths after cooling. Scientific instruments often incorporate glass components for their transparency and chemical resistance. Spectrophotometers use glass or quartz cuvettes to hold samples for analysis. Optical instruments use glass lenses and prisms to manipulate light. The glass for these applications must be of high optical quality, free from bubbles, stones, or other defects that would scatter or absorb light. The polishing of optical glass is an extremely precise process. The glass surface must be shaped to exact curves and polished to a smoothness measured in fractions of a wavelength of light. The polishing is done in stages, with progressively finer abrasives removing smaller and smaller amounts of material. The final polishing creates a surface that transmits or reflects light with minimal scattering. Glass art objects can range from small ornaments to large architectural installations. The techniques used vary widely, from traditional glassblowing to modern kiln-forming methods. Artists exploit glass's unique properties, including its transparency, color possibilities, and ability to capture and transmit light. The interplay between opacity and transparency, between color and clarity, creates visual effects unique to glass. Sculptural glass art may combine multiple techniques and materials. Cast glass sections might be assembled with blown or slumped components, creating complex three-dimensional forms. Metal, wood, or stone might be incorporated along with glass, combining materials with different properties into unified works. The technical challenges of working with glass become part of the artistic process. The gallery presentation of glass art takes advantage of lighting to reveal the material's qualities. Translucent pieces glow when backlit, colored glass projects hues into surrounding space, and transparent glass creates effects of reflection and refraction. The way light interacts with glass is central to how glass art is experienced and appreciated. Historical glass objects provide insights into ancient glassmaking techniques. Roman glass vessels show the skill achieved by early glassblowers working with simple tools and wood-fired furnaces. Medieval stained glass windows demonstrate sophisticated understanding of color and composition. Studying historical glass helps modern makers appreciate the development of techniques over centuries. Archaeological glass often shows effects of long burial, with surfaces altered by interaction with soil and groundwater. The glass may develop iridescent surfaces or become opaque from weathering. These changes do not affect the underlying bulk glass composition but create surface layers with different properties. Conservation of archaeological glass requires understanding these weathering processes to prevent further deterioration. Glass conservation involves stabilizing glass objects to prevent further damage while preserving their historical and aesthetic value. Broken pieces may be reassembled, using adhesives that are strong enough to hold the glass but reversible enough to allow future treatment if needed. Missing sections might be filled to restore structural integrity while making the restoration visually distinguishable from original material. The study of ancient glass chemistry reveals information about trade routes and technological knowledge of past civilizations. Analysis of glass composition can identify where raw materials came from and whether glassmakers had access to certain substances. Changes in composition over time show the evolution of glassmaking knowledge and the availability of different materials in different periods and regions. Glass continues to find new applications as technology advances. Flexible glass thin enough to bend is being developed for electronic displays that can fold or roll. Glass with embedded sensors can detect touch, temperature, or other stimuli. Bioactive glass can bond with bone tissue and is used in medical implants. The development of new glass compositions and forms continues to expand the material's possibilities. Research into glass structure seeks to understand how the arrangement of atoms affects properties. While glass is amorphous rather than crystalline, its atomic structure is not completely random. There are patterns and preferences in how atoms connect to each other, creating short-range order even without long-range crystalline patterns. Understanding these structures helps in designing glasses with specific properties. Computer modeling allows researchers to simulate glass behavior at the atomic level. These simulations can predict how changing composition will affect properties, reducing the need for extensive experimental trials. The models help optimize glass formulations for particular applications, whether maximizing strength, controlling thermal expansion, or achieving specific optical properties. The environmental aspects of glass production include energy consumption, emissions, and raw material use. Melting glass requires substantial energy, traditionally from fossil fuels. Though some facilities are incorporating renewable energy sources, the batch materials must be mined and transported, each step having environmental impacts. Recycling glass reduces these impacts by lowering the temperature needed for melting and reducing the need for virgin raw materials. Glass packaging offers environmental advantages in some contexts because it is inert and can be recycled indefinitely without loss of quality. Glass containers do not transfer flavors or chemicals to their contents, maintaining product quality. The weight of glass compared to alternative packaging materials affects transportation energy, creating trade-offs that must be considered in evaluating environmental performance. The circular economy approach to glass emphasizes keeping materials in use through reuse and recycling rather than disposal. Returnable glass bottles can be washed and refilled many times before recycling becomes necessary. When recycling does occur, the glass can be melted and reformed into new containers repeatedly. This circularity reduces the environmental footprint of glass products over their full life cycle. Collection systems for glass recycling vary by region, affecting recycling rates and the quality of recovered glass. Single-stream recycling, where glass is mixed with other materials, can lead to contamination and breakage, reducing the value of the recycled glass. Separate collection of glass, especially with color sorting, provides cleaner cullet that can be used in higher quality applications. The processing of recycled glass involves sorting, cleaning, and crushing. Magnets remove ferrous metals, while other processes separate non-ferrous metals, ceramics, and other contaminants. The clean glass is crushed to a consistent particle size, creating cullet ready for use in glass production. The quality of the cullet depends on how thoroughly contaminants have been removed. Some contaminants in recycled glass are particularly problematic. Ceramics and stones do not melt at the temperatures used for glass, so they remain as solid inclusions that create defects. Heat-resistant glass like borosilicate has different melting characteristics than container glass and can cause issues if mixed in. Careful sorting and inspection minimize these problems, but some contamination is difficult to eliminate completely. The market for recycled glass includes both glass manufacturing and alternative uses. Glass manufacturers prefer clean, color-sorted cullet for making new containers or fiberglass. Mixed-color cullet might be used for fiberglass insulation where color is not important. Crushed glass can also be used as aggregate in construction materials, as abrasive grit, or in water filtration systems. Fiberglass insulation is made from glass fibers that trap air and reduce heat transfer. The glass is melted and formed into fibers that are collected into bats or loose fill. The fiber structure creates millions of small air pockets that provide the insulating value. Fiberglass insulation is widely used in buildings to reduce energy consumption for heating and cooling. Fiberglass reinforcement for composites uses glass fibers with higher strength than those for insulation. The fibers are arranged in mats or woven into fabrics that can be impregnated with resin to create strong, lightweight composite materials. These materials are used in boat hulls, automotive parts, wind turbine blades, and many other applications where strength and lightweight are important. The combination of glass fibers with resin creates materials with properties different from either component alone. The glass provides tensile strength and stiffness, while the resin holds the fibers in position and transfers loads between them. The composite can be molded into complex shapes that would be difficult or impossible to create from either glass or resin alone. Glass foam is a cellular material made by heating crushed glass with a foaming agent. The agent releases gas as the glass softens, creating bubbles throughout the material. When cooled, the result is a lightweight material with closed cells, providing insulation and buoyancy. Glass foam can be used in construction insulation or as lightweight film material. Glass beads are small spheres made by feeding crushed glass through a flame or heated zone where surface tension pulls the molten glass into round shapes. The beads cool and solidify while falling, creating hard spherical particles. Glass beads are used in reflective road markings, as filler in composite materials, in water filtration, and in blasting processes where softer abrasive action is needed than sand provides. Specialty glass compositions serve niche applications where common glass formulations are inadequate. Radiation shielding glass contains lead or other heavy elements that absorb X-rays and gamma rays, protecting people from radiation exposure. The glass must be thick enough and contain sufficient shielding material to provide the needed protection while remaining transparent enough for visibility. Photochromic glass darkens when exposed to ultraviolet light and becomes clear again when the UV source is removed. The effect comes from silver compounds embedded in the glass that change form in response to UV exposure. The glass is used in eyeglasses that darken in sunlight and clear indoors, providing automatic adjustment to lighting conditions. Electrochromic glass changes its light transmission properties when an electric current is applied. The glass contains layers that can change their absorption or reflection characteristics reversibly. This allows windows to be darkened or cleared electronically, providing control over light and heat transmission. The technology is used in smart windows and in applications like aircraft windows and rearview mirrors that can dim to reduce glare. Glass ceramics are materials that start as glass but are then heat-treated to cause controlled crystallization. The resulting material combines glass and crystalline phases, gaining properties from both. Glass ceramics can have very low thermal expansion, making them resistant to thermal shock. They can be stronger than ordinary glass and can be made opaque or translucent rather than transparent. The production of glass ceramics involves carefully controlled heat treatment after the glass is formed. The temperature and time of the heat treatment determine how much crystallization occurs and what crystal phases form. Different heat treatments can produce glass ceramics with different properties from the same initial glass composition. The process allows fine-tuning of properties to match application requirements. Cookware made from glass ceramics can withstand the thermal shock of going from refrigerator to hot oven without cracking. The low thermal expansion means temperature differences across the material create minimal stress. The material is also resistant to chemical attack from foods and cleaning products. These properties make glass ceramic cookware durable and versatile. Dental glass ceramics are used for crowns, inlays, and other restorations. The material can be colored and shaped to match natural teeth while providing strength and durability. The glass ceramic bonds to tooth structure and is biocompatible, meaning it does not cause adverse reactions in the mouth. The material can be milled or molded to create precise fits for each patient. Glass for optical applications ranges from simple lenses to complex assemblies in cameras and microscopes. Each glass element must be made to precise specifications for shape and surface quality. The glass composition affects how light passes through, with different glasses having different refractive indices and dispersive properties. Optical designers select specific glasses to achieve desired performance. Anti-reflective coatings on glass reduce light loss through reflection, improving transmission through optical systems. The coatings are thin films that interfere with reflected light waves, causing them to cancel each other out. Multiple layers with different thicknesses and compositions can provide anti-reflection over a broad range of wavelengths. The coatings are applied using vacuum deposition techniques that build up the layers atom by atom. Glass in solar panels protects the photovoltaic cells while allowing light to reach them. The glass must have high light transmission, especially in the wavelengths that the solar cells can convert to electricity. It must also be strong enough to withstand weather conditions and resist soiling and degradation over years of outdoor exposure. Special surface treatments can make the glass self-cleaning or reduce reflection to increase the light reaching the cells. Bulletproof glass is a layered assembly of glass and plastic designed to stop projectiles. Multiple layers of glass alternate with plastic interlayers that absorb energy from impacts. The glass layers crack when struck but are held in place by the plastic, which also catches the projectile. The thickness and number of layers determine what level of threat the assembly can defeat. Aircraft windows must withstand pressure differences between cabin and outside air while providing clear visibility. They are made from multiple layers of acrylic or glass with specific thicknesses designed to prevent crack propagation. The inner and outer layers are separated by an air gap in some designs, providing insulation and redundancy. Heating elements prevent ice formation that would obscure visibility. Aquarium glass must support the weight of water while remaining transparent. Large aquariums use thick glass or acrylic panels that are precisely fabricated and assembled. The edges are usually polished and the panels joined with structural silicone that bonds the glass while remaining flexible. The assembly must be watertight and strong enough to contain potentially thousands of gallons of water safely. Glass blocks are hollow glass units used in construction to provide light transmission while offering privacy and structural strength. The blocks are formed in molds and partially evacuated before sealing, creating a partial vacuum that provides insulation. Glass block walls can be load-bearing and offer better insulation than single-pane glass while allowing light to pass through. Decorative glass treatments include various techniques for modifying appearance. Acid etching creates permanent matte or frosted effects. Sandblasting can create deeper texture and patterns. Applied films can add color or pattern while remaining removable. Fused glass techniques bond colored glass pieces together. Each treatment offers different aesthetic possibilities and levels of permanence. The maintenance of glass involves cleaning and occasional repair. Cleaning methods must be appropriate for the type of glass and any coatings present. Some glass has protective coatings that can be damaged by abrasive cleaners or harsh chemicals. Clear glass shows dirt and fingerprints readily, requiring regular cleaning to maintain appearance. Proper maintenance extends the life and preserves the clarity of glass installations. Repair of broken glass depends on the type and application. Laminated glass can sometimes be repaired if only one layer is damaged, by filling cracks with resin. Tempered glass cannot be repaired and must be completely replaced if damaged. Specialty glass like stained glass can sometimes be repaired by removing and replacing damaged pieces. The decision to repair or replace depends on the extent of damage and the value of the original. Safety considerations with glass include preventing injury from breakage and ensuring installations are secure. Laminated or tempered glass reduces injury risk compared to ordinary glass. Proper installation prevents glass from falling out of frames. Marking large glass panels makes them visible, preventing people from walking into them. Building codes specify where safety glass must be used. Glass waste from manufacturing processes can often be recycled back into production. Trimmings, broken pieces, and out-of-specification products are collected and returned to the batch preparation area. This closed-loop recycling is efficient because the waste glass is already clean and sorted, requiring minimal processing before reuse. It reduces both waste disposal and raw material costs. The future of glass may include new compositions and forms that expand its applications. Research into metallic glasses, which have amorphous metal structures, could create materials with unique combinations of properties. Bioactive glasses that can integrate with living tissue continue to be developed for medical uses. Glass with embedded nanoparticles could have enhanced or tunable properties for optical or electronic applications. Manufacturing processes continue to evolve toward greater efficiency and precision. Automation reduces labor costs and improves consistency. Computer control systems optimize operating parameters in real time based on sensor feedback. Energy efficiency improvements reduce the environmental impact and operating costs of glass production. These advances help the glass industry remain competitive and sustainable. The versatility of glass ensures its continued relevance across many industries. Its transparency makes it irreplaceable for windows and containers. Its chemical inertness makes it ideal for storing sensitive substances. Its formability into precise shapes enables optical and electronic applications. Its strength, when properly treated, supports structural uses. No single alternative material provides all these properties. The tradition of glassmaking connects modern production to ancient practices. While technology has advanced dramatically, the fundamental principles of melting sand and other materials to create glass remain the same. The craft knowledge of glassblowers continues alongside industrial production, maintaining artistic traditions. This connection between past and present enriches the understanding and appreciation of glass. Communities built around glass production develop specialized knowledge and skills that pass through generations. Workers understand the subtleties of how glass behaves under different conditions. Maintenance personnel know the quirks of specific equipment. Designers push the boundaries of what can be created. This accumulated expertise sustains the industry and enables continued innovation. The economics of glass production involves balancing costs of raw materials, energy, labor, and capital equipment against the value of products produced. Efficiency in each area contributes to profitability and competitiveness. Energy costs are significant due to the high temperatures required for melting. Automation reduces labor costs but requires substantial capital investment. Successful operations optimize these factors. Glass markets vary in size and growth rates. Container glass for food and beverage packaging is a mature, stable market. Flat glass for construction fluctuates with building activity. Specialty glasses for electronics and other high-tech applications may offer higher margins but smaller volumes. Glass producers may focus on specific markets or diversify across multiple segments to balance risk and opportunity. Global trade in glass products moves materials from producing regions to consuming regions. Shipping costs must be considered against the value of the products, with lightweight specialty glasses more economically shipped than heavy bulk products. Some glass production has shifted to regions with lower energy or labor costs, while specialized production remains in regions with technical expertise. Quality standards for glass products ensure consistency and performance. Industry standards specify requirements for strength, clarity, dimensional tolerances, and other properties. Third-party testing verifies compliance with standards. Certification programs provide assurance to customers that products meet required specifications. Standards facilitate trade by providing common benchmarks recognized across markets. Innovation in glass products often comes from understanding customer needs and developing glasses that meet those needs better. Lighter glass reduces material use and shipping costs. Stronger glass allows thinner sections for the same performance. Glass with improved insulating properties reduces energy consumption in buildings. These improvements deliver value that justifies investment in development and sometimes premium pricing. The relationship between glass producers and their customers ranges from commodity transactions to collaborative partnerships. Commodity products like standard containers or flat glass are purchased primarily on price and availability. Specialty products may involve close collaboration to develop glasses meeting specific performance requirements. Long-term relationships provide stability for both producers and customers. Glass production requires sustained capital investment in furnaces, forming equipment, and support systems. Furnaces have limited operating lives and must be rebuilt periodically, requiring significant expenditure. Process improvements may require equipment upgrades. Expanding capacity requires additional furnaces and forming lines. The capital-intensive nature of the industry creates barriers to entry but also provides advantages to established producers. Environmental regulations affect glass production through limits on emissions, effluent discharge, and waste disposal. Compliance requires investment in control equipment and monitoring systems. Regulations drive improvements in efficiency and cleaner processes. The industry has generally adapted successfully to increasingly stringent requirements while maintaining productive capacity. Worker safety in glass plants addresses hazards from high temperatures, molten materials, heavy equipment, and noise. Safety programs train workers in proper procedures and provide protective equipment. Engineering controls isolate hazards where possible. A strong safety culture emphasizes prevention and continuous improvement. Safe operations protect workers and reduce costs from injuries and lost time. The glass container industry supplies packaging for beverages, food, pharmaceuticals, and cosmetics. Glass containers offer several advantages, including complete impermeability to gases and liquids, chemical inertness that prevents interaction with contents, and recyclability. The aesthetic appeal of glass and its association with quality make it preferred for premium products despite higher costs than some alternatives. Wine and spirits are traditionally packaged in glass because the material does not affect taste or aroma. The bottles become part of the product identity, with distinctive shapes and colors associated with particular brands or regions. Heavy glass bottles convey quality and luxury, even though the weight serves no functional purpose. The packaging becomes part of the consumer experience. Food packaging in glass ranges from jars for preserved foods to bottles for sauces and condiments. The visibility through clear glass allows consumers to see the product, which can be an advantage for appealing foods. The hermetic seal possible with glass closures enables long shelf life without refrigeration for many products. Glass jars can be reused by consumers for home canning or storage. Pharmaceutical packaging in glass protects medicines from contamination and degradation. The inertness of glass ensures no interaction with drug compounds. Glass can be sterilized by heat without damage, supporting aseptic processing. Regulatory requirements for pharmaceutical containers are stringent, and glass has a long history of safe use that satisfies these requirements. Perfume and cosmetics often use glass bottles for their aesthetic qualities and premium image. The weight and clarity of glass convey luxury and quality. Glass bottles can be decorated with elaborate designs, colors, and closures that enhance visual appeal. The packaging contributes to the brand identity and consumer perception of the product value. The closure systems for glass containers must provide adequate sealing while allowing convenient opening. Screw caps with gaskets or liners create tight seals for carbonated beverages and products requiring airtight closure. Cork stoppers for wine bottles provide traditional appeal and allow minute gas exchange that some consider beneficial for wine aging. Metal caps for beer bottles seal securely and are easily removed. Child-resistant closures for pharmaceuticals and some household products make opening difficult for young children while remaining accessible to adults. These closures use mechanisms that require specific manipulation to open, such as pressing while turning. The designs must meet testing standards that verify effectiveness while allowing most adults to open the containers. Tamper-evident features on closures show whether a container has been opened since filling. Bands that break upon first opening, sealed liners that must be removed, or other indicators assure consumers that the product has not been accessed. These features became standard after incidents of product contamination highlighted the need for visible evidence of tampering. The filling of glass containers with product must be done carefully to avoid damage and ensure proper sealing. Automated filling lines move containers through cleaning, filling, and capping stations at high speeds. The containers must be stable throughout the process, supported and guided without excessive force that could cause breakage. Fill levels must be accurate to meet legal requirements and consumer expectations. After filling, glass containers are usually labeled to identify the product and provide required information. Labels may be pressure-sensitive adhesives applied as sleeves or spot labels, or they may be screen-printed directly onto the glass. The labeling must adhere securely and remain legible throughout distribution and use. High-quality printing enhances product appearance and brand recognition. Packaging filled glass containers for shipment requires protecting against breakage. Dividers separate containers within boxes, preventing contact between glass surfaces. Cushioning materials absorb shocks during handling and transportation. Shipping containers must be strong enough to support stacking without crushing. Proper packaging reduces breakage rates and ensures products reach customers intact. The weight of glass containers affects shipping costs and environmental impact from transportation. Lightweighting efforts seek to reduce glass weight while maintaining adequate strength and quality. Computer modeling and testing validate lighter designs before production. Successful lightweighting reduces materials use and energy consumption throughout the supply chain. Distribution of glass containers involves warehousing and logistics to deliver products when and where needed. Just-in-time delivery minimizes inventory costs for customers but requires reliable supply and short lead times from producers. Regional distribution centers allow producers to serve distant markets while maintaining service levels. Efficient logistics are essential for commodity products where margins are thin. The retail display of products in glass containers takes advantage of transparency and aesthetic appeal. Products are positioned to maximize visibility and attract consumer attention. Lighting enhances the appearance of glass packaging. The weight and rigidity of glass allow stable stacking and display arrangements. Premium products in distinctive glass packaging often receive prominent placement. Consumer use of glass containers includes considerations of convenience, safety, and disposal. Resealable containers allow multiple uses while maintaining freshness. The weight of glass can be a disadvantage for portability but conveys quality. Glass does not retain odors or stains from previous contents, supporting reuse for other purposes. Recycling programs accept glass containers, making disposal environmentally responsible. The reuse of glass containers by consumers extends product life and reduces waste. Jars can store dry goods, leftovers, or craft supplies. Bottles can be refilled with homemade beverages or used as decorative items. The durability of glass supports repeated washing and reuse. Some consumers specifically seek glass containers for their reusability. Commercial reuse systems for glass bottles, such as returnables for beverages, require infrastructure for collection, cleaning, and redistribution. The bottles must be durable enough to withstand multiple cycles of use and washing. Standardized bottle designs allow multiple brands to use the same containers, improving economics of reuse systems. Return deposit systems incentivize consumers to bring bottles back rather than discarding them. The washing of returnable bottles must remove all residues and contaminants while not damaging the glass. High-temperature washing with detergents and thorough rinsing prepares bottles for refilling. Inspection systems check for cracks, chips, or remaining contamination, rejecting bottles that do not meet standards. Properly washed returnables are hygienically equivalent to new bottles at lower cost and environmental impact. Refillable bottle systems are most common for beverages consumed locally, reducing transportation distances for the heavier returnable containers. Beer, milk, and soft drinks have historically used returnable systems in many markets. Economic and cultural factors influence whether returnable systems persist or are replaced by single-use containers. Returnable systems require consumer participation and convenient return locations to function effectively. The flat glass industry supplies construction, automotive, and other markets with sheet glass in various sizes and types. Float glass production creates the basic material, which then may be processed further for specific applications. Coating, tempering, laminating, and other treatments add value and functionality to the basic float glass substrate. Architectural glass includes windows, doors, curtain walls, and other applications in buildings. The glass must meet building codes for strength, safety, and often energy efficiency. Insulating glass units are standard in climates where thermal control is important. Coatings control solar heat gain and heat loss, reducing energy needed for heating and cooling. Proper specification and installation ensure glass performs as intended. Commercial building facades often feature extensive glass areas that create modern aesthetic while admitting daylight. The engineering of these facades must address wind loads, thermal stresses, and structural support of large, heavy glass panels. Mullion systems or structural glazing techniques attach glass to building frames. The result is architecture that would be impossible without modern glass technology. Residential windows have evolved toward better energy efficiency through improved glass and frame systems. Double or triple glazing with low emissivity coatings significantly reduces heat transfer compared to single-pane windows. Gas fills between panes provide additional insulation. Proper installation with weather sealing prevents air leakage that would compromise performance. Skylights and overhead glazing bring natural light deep into buildings, improving ambience and reducing electric lighting needs. The glass must support its own weight plus snow and wind loads while remaining transparent. Laminated or tempered glass provides safety in case of breakage. Condensation control and thermal performance require attention to avoid moisture problems. Interior glass applications include partitions, doors, and decorative elements that provide openness and light transmission while defining spaces. Tempered glass ensures safety in locations where human contact is possible. Frosted or patterned glass provides privacy while allowing light to pass. Glass in interiors contributes to aesthetic quality and spatial perception. Shower and bath enclosures use tempered glass for safety and durability. The glass must resist water and cleaning chemicals without degrading. Hardware systems allow doors to operate smoothly while supporting the weight of glass panels. Proper sealing prevents water leakage while allowing access for cleaning. Glass railings provide safety barriers with minimal visual obstruction, commonly used on balconies, stairs, and elevated walkways. The glass must be thick enough and properly supported to act as a structural barrier preventing falls. Laminated glass holds together if broken, maintaining barrier function even when damaged. Mounting systems must securely attach glass to supporting structure while allowing installation and replacement. The maintenance of architectural glass involves regular cleaning and inspection. Exterior glass exposed to weather accumulates dirt and pollutants that reduce clarity and appearance. Access for cleaning high glass areas requires special equipment and trained personnel. Inspection identifies damaged seals, cracks, or other issues that may require repair before they worsen. Replacement of failed insulating glass units is a common maintenance task in buildings. The seal failure allows moisture to enter between the panes, causing fogging that cannot be cleaned away. Replacement involves removing the failed unit and installing a new one, requiring careful measurement to ensure proper fit. Modern units should last many years before seal failure occurs. Glass in historic buildings may be original material that has aged and developed characteristics valued for authenticity. Old glass may have waves, bubbles, or slight color variations that distinguish it from modern float glass. Preservation efforts seek to retain original glass where possible, repairing rather than replacing. When replacement is necessary, historically appropriate glass may be sought to maintain character. The automotive glass industry serves vehicle manufacturers and the replacement market with windshields, side windows, and rear windows. Each piece of glass is precisely formed to fit specific vehicle models. The complex curves of modern automotive glass require sophisticated forming processes and quality control to ensure proper fit and optical quality. Windshield installation involves bonding the glass to the vehicle structure with polyurethane adhesive. The adhesive must be applied uniformly around the perimeter and allowed to cure properly. The windshield contributes to vehicle structural rigidity and must remain securely attached in a crash. Proper installation is critical for both function and safety. Automotive glass repair addresses small chips and cracks that can be fixed without full replacement. Resin is injected into the damage under pressure, filling the void and bonding the separated glass. When cured, the resin restores most of the original strength and clarity. Successful repair depends on addressing damage early before it spreads. Advanced automotive glazing includes features like rain sensors, heating elements, and antenna embedded in glass. These features integrate multiple functions into the windshield, reducing the need for separate components. The glass becomes a smart surface that senses and responds to conditions, enhancing vehicle functionality and occupant comfort. The glass industry workforce includes diverse roles from furnace operators to quality inspectors to researchers developing new products. Each role requires specific knowledge and skills. Training programs prepare workers for their responsibilities. Experienced workers mentor newcomers, passing along practical knowledge. The competence of the workforce directly affects product quality and operational efficiency. Glass industry trade organizations support member companies through technical information sharing, advocacy, and standards development. The organizations bring together competitors on issues of common interest, fostering industry progress. Conferences and publications disseminate new knowledge and best practices. Industry standards developed through these organizations facilitate commerce and ensure quality. Education in glass science and engineering prepares the next generation of industry professionals and researchers. University programs teach the fundamentals of glass chemistry, physics, and processing. Students learn through coursework and hands-on laboratory experience. Graduates enter careers in manufacturing, research, or related fields, applying their knowledge to advance the industry. Research in glass continues at universities, national laboratories, and corporate facilities. Basic research explores fundamental questions about glass structure and properties. Applied research develops new compositions and processes for commercial applications. The research community shares findings through publications and conferences, building on each other's work to expand knowledge. The glass industry supports communities where facilities operate through employment, taxes, and economic activity. The jobs provided support families and contribute to local economies. Facilities purchase supplies and services from local businesses. The presence of glass industry can anchor communities, providing stability through economic changes. Corporate citizenship through community involvement strengthens these relationships. Glass as a material has been part of human civilization for thousands of years, its uses evolving as technology advances. From ancient beads and vessels to modern architectural walls and fiber optic networks, glass serves ever-expanding roles. The material continues to find new applications as understanding of its properties deepens and processing capabilities improve. Glass seems likely to remain essential far into the future. The production of glass continues in factories around the world, furnaces glowing with molten material day and night. The transformation from sand to glass proceeds through familiar steps refined over generations. New pieces of glass emerge constantly, joining the vast quantity already in use. The cycle of production, use, and recycling continues, with glass serving human needs in forms both practical and beautiful, transparent and solid, ancient in origin yet thoroughly modern in application.